Good morning, everybody. We're going to start off with a bunch of problems. Somebody get them drawn up on the iPad, and then we will get moving. So once they're up, I'm going to give you guys about 10 minutes to work through them. All right, I'm going to give you guys till around 9:28 to go through these, and then we will go through them together. All right, so let's get started on these. We're going to be referring a lot to that table we created on Friday. So our first one here is actually a group 6. Because we have 4 substituents on the nitrogen, it's positively charged, making this strongly deactivating. And a meta director. This would be contrary to if we only had 2 methyl groups on there. That would actually be a group 1. But because we have a total of 4 substituents on our nitrogen, it makes it a group 6 here. So HNO3 and H2SO4 at the nitro group. Group 6 makes it a meta director. We're going to add NO2 to our meta position. For our next one, we have a methyl group here, which is group 3, which is an ortho para director. Bromine is pretty small, so we can add both ortho and para. It's not going to be overly selective for one versus the other. So we're going to end up with 2 products for this one. Same thing with the next one. OH is a group 1. Which is also ortho para. Cl is pretty small. We're going to end up with 2 different products for this one. We're either going to add to our ortho or our para position. All right. We're getting into some larger molecules on this next one. So we've got, I'll draw a little line here. Cl, which is our group 4, which is still in our ortho para category. Fuming H2SO4 adds a sulfate. Sulfates are pretty large, so most likely this is going to go para just due to a size constraint. This could also form chloro, ortho, but I would expect, because how large a sulfate is, that para position is going to be favored. And you can kind of see if you draw it out. That there should be a pretty strong interaction between this Cl and this oxygen here. It'd be difficult to kind of fit that into that spot. All right, now we're starting to get into multiple groups here. This nitrogen still has a lone pair, as opposed to the one up top with a positive charge. So that puts this one into group 1. Our methyl here is a group 3, which means our group 1 is our higher priority. So the ortho and para positions relative to this nitrogen here would be this and this. The last ortho is blocked by that methyl group, so we can kind of ignore it. Cl2 is pretty small. This is probably going to end up giving us two products. Either chlorine or ortho relative to the nitrogen, or para. All right, we've got a group 1 versus a group 2 here. Group 1 or ortho para still. So group 1 will be the priority. Its para is blocked, which means it has to add ortho. Making our product this here. All right, these are all group 2s, and it's symmetrical. The ortho para directors, doesn't really matter which one. We add 2. Technically, these are all the same due to symmetry. Oh, we had excess up top. I'll go back and do that one in a minute. Okay. Because it's symmetrical, you could add any of these positions. So I'm just gonna draw this one on top, like so. All right, we've got a group 3. And then 2 group 5s. Group 3 is to be a higher priority. It's an ortho para director. Currently, the ortho groups are both blocked, which means the only one that's left is the para one. Giving us this product here. Let's go back to this one that was in excess. Oh yeah, sorry. I wrote these down wrong. NO2 is group 6, not group 5. Oh. Do we have that anywhere else? No. Okay. Let's go back to this one here. I did it. I forgot I wrote down excess here. So these are just the answers if it was an excess. If it is an excess, I'm just going to redraw it. All right, we had a group 1 and group 3. it can initially add either ortho or para. But because we're in excess, it'll add again. So for this one on the left, it would add to the para. One on the right, it would add ortho. It give us the same product in both cases. Just dichlorination. Yeah, so if it's in excess, you're just going to get one product because you're just going to chlorinate in every position you can. So another example of this would be we would think of this as a group 3. It can add either ortho or para. For doing it in excess, it's just going to add to all of them. So we would get this product. Okay, we are going to cover a small amount of, yes, this would be the final product. A small amount of chapter 22 today. There's a few reactions in chapter 22 that deal with aromatic rings. So we are going to go through those. And they all involve what's referred to as the diazonium salt, something you may have done at lab at this point. And it starts with reactions we've done before. So if we take HNO3, H2SO4, we can add a nitro group. Throwing in iron, HCl, will let us reduce this down to an amine. We talked about this on Friday. From here, if we add in NaNO2 in HCl, this is going to let us make what's referred to as a diazonium. So this is from chapter 22, section 2210. And then I'll do it the other way first. From here, we can do a bunch of different reactions to aromatic rings. So, and we're not going to cover mechanisms for any of these because they're complicated. Most of these are going to be fairly boring. If we add in copper and either chlorine or bromine, we can make either a chloride or a bromide. We already know how to do these reactions. Not that exciting. If we add in HBF4 and water, this lets us add a fluorine. And this is useful. This is our only way we know how to add fluorine to an aromatic ring. So I'm going to put a star next to this one. We can make an alcohol or an OH. We can make phenol if we add in water and heat. Currently, this is the only way we know how to do it, but we will learn a new one in chapter 22. So, not 22, chapter 19, which we'll talk about tomorrow. Let's see. CuCN, so copper nitrile. Or if we just add in H3O plus or H3PO4. That's what I want. We can just add a proton here. So this is a series of reactions that are always going to be linked together. So for instance, if you wanted to fluorinate something, you're always going to go through this exact same pathway where you add HNO3, iron HCl, NaNO2, HCl, and then BH4 and water. All right. So this is all of chapter 2 we're going to cover. We don't cover that much of it more either, even next exam. So this is almost pretty much all of 22 we cover in general. Let's take a look at a synthesis problem that uses this, though. I'm going to walk through this, and then we'll take a little bit of break today, or break, and come back and do some more synthesis and a few more reactions in chapter 18. So we've got a chlorine and a fluorine here. Our chlorine, if we were to add that first, it's a group 3, it's an ortho para director. We're going to run into the issue that we can't actually add to the position that we want to add it into, which is this meta one. So we're going to have to go through our fluorination pathway first. So our first step in our fluorination pathway, HNO3, H2SO4. From here, I have a meta director. And at this point, it's often best to just, if you have the ability to add your next group, just do it. Because alternatively, if we go to the next step, which is adding an iron HCl, now we're back to a group 1. And if we tried to add in our AlCl3, Cl2 AlCl3, we'd get a Cl in the wrong position. So we have a meta director here. This is a group 6. And this is going to let us just continue along that fluorination pathway and eventually get to our product. So adding in our iron HCl now. Nope. And then to get to a diazonium, we'll need to add in NaNO2, NaHCl, and to get to our final product, we'll throw in HBF4 in water. All right, we're going to do a bunch of synthesis problems when we get back, as well as a few more reactions that are in this chapter. So let's take till about 10 o'clock. So take about an 8-minute break and then meet back then. All right, welcome back. We are going to cover two more reactions in chapter 18 and then do a bunch of synthesis problems. So let's get started on these reactions. So these are going to fall into what is referred to as nucleophilic aromatic substitution. And it's mostly going to be useful for making alcohols or phenols. So a couple of different ways we can do this. The first one, I guess really the only one, is if we take chlorine here, as well as we need some sort of nitro group, either ortho or para to it. I'm going to draw it out. If we add in NaOH at this point, what we can have happen is a nucleophilic attack, kind of like an SN2. At our Cl center, we are going to have our electrons go all the way down to this nitrogen here, and then come back up to eliminate our chlorine and form our final product. This will only work if we have a Cl that is in either this ortho or this para position. If we don't, I can start on the left here, on the right. We're to get no reaction. Same thing if it's meta. You do your resonance arrows and it's meta, it actually never gets to the nitro group. So having either ortho or para will allow us to do this reaction. If it's meta or if we don't have a nitro group on there, it's just not going to work. All right, so that is nucleophilic aromatic substitution. It's a bit simpler than all those aromatic ones electrophilic aromatic substitutions we were doing earlier. The last reaction we're going to talk about is what's referred to as elimination addition reactions. So, elimination addition is going to be where we take a chlorinated compound. We're going to add in a nitrogen base, so we'll add in NaNH3 or NH2 and ammonia. This is going to allow us to do an elimination. So this NH2 minus here is going to let us pull off a proton and make a triple bond here, which is going to be pretty strained and pretty highly reactive. And from this point, it is a really good electrophile. So throwing in just more NaNH2 minus, which is in solution, this will attack our triple bond. Giving us a negative charge, which can pick up that other proton we picked up from the nitrogen in the first step to give us a product. These tend to get a little bit messy because you can attack on either side of your triple bond. So for instance, if we take toluene, adding in NaNH2, this will give us a triple bond. Here, from this point, we can have two different nucleophilic attacks. We can either have this attack or this attack. They're both going to lead to a product. So our blue pathway, once it reprotonates, is going to give us this amine versus the green one would give us this here. These are both major products. You should end up with an equal amount of both of them. So because you're making a triple bond, it can attack on either end of it. Doesn't matter which one. Oh crap, I forgot the chlorine in our starting material. Sorry. If your chlorine's here. I'm going to move the chlorine, and then we're going to end up with 3 products, although only one of them is going to be major. So that's going to be useful. This is when our chlorine is para to this methyl group. Doesn't have to be methyl group, but just drew it as one. If it's meta, this is going to complicate things further. So we're still adding an NaNH2. I'm going to draw it out twice, though, because there's going to be 2 different things we can make. So we can either get, in this first step, this triple bond, or this one. Because we have resonance, those double bonds can switch sides. We can make these 2 triple bonds. Each of these can lead to a product. So we can either have it attack at one of these 4 positions. Now, for this, we're actually going to get a major product. The reason for that is that this happens randomly. So we'd get 25%, 25%, 25%, and 25%. It just so happens that these 2 are the same. So because they're the same, we'd end up with 50% of this major product. Because we had 2 portions of 25% of it. And then these other 2 would be minors. Okay. I'm going to give you guys a couple of synthesis problems. We're going to kind of work through them one at a time. So I'm going to draw up all 3 of them, but then we will take about 5 minutes to the first one, talk through it, take about 5 minutes to the next one, talk through it, take about 5 minutes to the next one, talk through it. So there's going to be a couple of different ways to do these. They always have multiple answers. I don't know why I'm drawing 3 arrows. As long as it makes sense in terms of your group priorities, it can still work out. Just make sure you're not adding something meta when you have an ortho-para director as your highest priority group. All right, so I'm gonna give you guys till 10:21 to do this first one. After which we'll come back, work on that one. All right, the next, or we'll give you another 5 minutes to do the next one. If you get done with the first one, feel free to start the next one. Let's go 26. 10:20. Sorry, 10:20. 10:21. That's what I wanted. Yeah, so there's a couple of different ways to this first one. I'm going to go through one pathway. You might find a different one that works well also. If I act like I'm going to add this oops, nitro group. Oh my god. Come on. Nitro group first here. I need to go through my diazonium pathway to get there. So adding in HNO3, H2SO4. This lets me add a nitro group here. From this point, if I add, so I got a meta director here, I could chlorinate, get that chlorination product here. Adding in AlCl3 and Cl2. From this point, my priorities have switched. So I had a group 6. Which was a meta director. Now I've got a group 6 and a group 3, or 4. Group 4. Realistically, because my NO2 is pretty big. My group 4 is another para director. These two are pretty blocked. Most likely position if I was to add in BR2 would be to add here. So throwing in BR2, FeBr3. It's going to let us brominate. From here, we're just going through our pathway. We need to get to a diazonium in order to add in copper nitrate. So iron, HCl, gets us to an amine. NaNO2, HCl gets us to a diazonium. And then copper nitrate gives us to our final product. So a lot of these steps can be moved around. For instance, let's see, what are some other options here? All right, let's go through some things that aren't going to work. So if I instead here reduced first, so put there in FeHCl, I've got a group 1, it's an orthopara director. I could say, well, at least I can brominate, see what we got from there. So BR2, FeBr3. The amine is still my highest priority group. So at this point, if I try to chlorinate, it can only add to these positions, or we're going to get the wrong product. So this is going to be a dead end. Let's go back to the other one we did. So we threw in Cl2, AlCl3. We could have also reduced here and still gone through to our product. So if we added in iron, HCl, this amines a group 1. It'll add orthopara, so we can still add this Br to the correct position. Let's see. We could have brominated first. So if we add in Br2, FeBr3, I think this should still work. We've got an orthopara director. Most likely we don't want to chlorinate because it's going to give us 2 orthopara directors with the same amount of priority, which is going to be a mess. So adding in HNO3 first. Sorry, H2SO4 and HNO3. And then from here, our BR is our higher priority. It's an orthopara director. We could add this AlCl3 and Cl2. So a couple of different ways that work, a couple of different ones that don't. As long as you're following kind of your orthopara grouping rules, it should work out. So I'm gonna drop the next one, give you guys a few minutes or about 5 minutes to go through them, and then we will take another look at them. So let me clear this. Give you guys till 10:36. I'll also drop the last one in case any of you guys get through it quickly. Okay. Something to note is that if we just try to add this, group here, it's going to do a rearrangement. If you remember back to Friday, we talked about how because this would generate an actual carbocation, it would do a hydride shift. To get to this product instead. So in order to get that kind of group there, we'd have to add the acyl intermediate and then do a reduction. So something like this, followed by adding in zinc, mercury, HCl, can get us to this product and avoid that rearrangement. This one you can do in a lot of different orders. But I'm going to start by adding that group first. So if I was to add in my acyl chloride, doing my Fiedel-Crafts acylation, from here, I have a group 5. It's a meta director. In order to create these fluorines, I'm going to have to add nitro groups first. So if I added a nitro group now, it's going to go meta. I've got a group 5 and a group 6, so I still have a group 5 with our highest priority. I could do this again. From here, I can reduce this a couple of different ways. I can go straight to the alkane, or I could wait and do it later. It doesn't really matter. So adding in zinc, mercury, HCl will give me my carbon skeleton. And then I'm just going through my diazonium pathway. So FeHCl gets me to amines. NaNO2. NaHCl gets me to diazoniums. And then HBF4 in water would get me to the difluoros. You could add the nitro groups first because there's a group 6. So you could either dinitrate or add a nitro group, do the Fiedel-Crafts, do another nitro group. Any of that order has kind of worked out fine. The only thing you really can't do would be after this first stage. Red. If we reduce now, what do you think? This is going to give us an orthopara director, and then we're not going to be able to get the meta to each other. So as long as you added meta directors continuously, you can create a pathway that works for this one. All right, I'm going to redraw the last one. Give you guys till 10:47, and then we'll go through it. All right, so this one probably has the most unique options for how to do this one. I'm going to start off with doing it as a nucleophilic aromatic substitution. This is not necessarily, it's not the only way to do it, but it's maybe the quickest way to do it. So if I was to throw in AlCl3 and Cl2, I could chlorinate, followed by HNO3, H2SO4, this is going to set me up to do that reaction we talked about a little bit earlier. So if we have a para NO2 to a Cl, if we throw in NaOH, we can do that addition elimination, nucleophilic aromatic substitution we talked about. To get to here. You could also go through a diazonium pathway instead. So adding an HNO4 all the way to diazonium and then throwing in H2O and heat could get you to an alcohol. From here, I've got a group 1 and a group 6. I could add my acyl chloride and now I just need to go through my diazonium pathway to get to my final product. So FeHCl gets me to an amine, NaNO2, HCl, get me to my diazonium. And then HbF4 and water and get to your final product. And there's going to be a couple of different ways that also work for this. You could have gone through the entire diazonium pathway and then added the acyl group. Or you could have added the fluorine first. As long as it works in our normal grouping and orthopara directing manner, it will be fine. So I'm going to stop here for today. Tomorrow we are going to do chapter 19. So I should see you guys all on recitation later. So have a good, I don't know, about 25 minutes or an hour and 25 until I'll see you again.